This is an overview of exercise 1618. This is the final result. We'll work backwards and then forwards again. The main idea is to produce a large DC current along this channel. The smaller DC currents make the larger DC currents happen. There's voltages that are very important, but zero resulting current, which is a bit strange. What made all of this happen was a 24-volt transformer input 120 volts AC and creating 24 volts AC at the secondary. These two rectifier diodes will create a full wave signal at this point. That is, they would if this capacitor weren't there. Now the capacitor is there, which will smooth out these positive pulses and make DC that we talked about earlier. Now, these are the equations that explain the things you really want to know. That is, this zener diode has a certain voltage rating, and the voltage rating means that the voltage across this diode, VA, is the diode rating voltage, diode voltage rating. So the whole purpose for this diode is to fix a voltage reference, VA, right here, even though this DC larger voltage might be fluctuating. This voltage will be held constant, ideally constant, even though there's fluctuation of DC voltage here. Now, the transistor opamp combination will do whatever it needs to do in conjunction with this feedback resistor to create a voltage here that's the same as the voltage there. So the voltage here is fixed at VA. If the voltage is VA there, then that means there will be a current through R3, which is VA divided by R3. And that current all has to come through this resistor because there was no current here. Knowing the current through this resistor, we can calculate V4, the voltage across this resistor, is I3 times R4. Now, since we know the voltage is VA here, and there's a voltage rise across this resistor, then V5 will be equal to VA plus V4. Knowing the voltage V5, we can calculate the current through R5, V5 divided by R5. This is a DC power supply circuit from 120 20 volts. AC input. A center tap 24 volts. AC at the secondary, but because it's center tapped and because there are two rectifier diodes, the voltage here is full wave rectified. With respect to 0, the voltage pulses only go positive. The voltage would be that at this point if it weren't for the capacitor. The capacitor will smooth out these bumps and make DC. Ideally, there will be a DC voltage here because of primarily the capacitor smoothing out the full wave rectified signal. The DC signal here will cause a relatively small current through this zener diode. The current goes backwards through the zener diode, and then a smaller current through this resistor and through that zener diode. The voltage of this zener diode is VA. That voltage fixes this reference voltage for the op-amp. The op-amp and transistor and feedback resistor will do what they have to do to create a voltage here the same as the voltage there. Because the voltage is VA here, that means the voltage VA across R3, then the current through R3 is VA divided by R3. Let's call that I3. There's no current into the ideal op-amp, and so all of that current has to come through R4. Therefore, the voltage across R4, positive on the high side, negative on the low side, will be equal to I3 times R4. Because we know the voltage at this point is VA, and there's a voltage rise across that resistor, then the voltage is V5 at that point. V5 is VA plus V4. Knowing the voltage across this resistor is V5, then the current through R5 is V5 divided by R5. All of that current comes through the transistor plus a little tiny bit of base current that's required to turn that transistor on. But originally, all of this relatively large current is coming from the DC signal produced here. The smaller signals that drive the op-amp and drive the base of this transistor are the controlling signals. But this is a DC, the inner workings of one DC power supply. Plug it into 120 volts AC and get any voltage we want out here within the limits V5 just by turning this potentiometer.